Hey everybody, welcome to the tutorial session number 1, which is entitled Training Deep Neural Networks from Zero to Hero, Avoiding Pitfalls and Going Beyond. My name is Sandra. I am professor in the Institute of Computing in the University of Campinas, Unicamp in Brazil. And today I'm going to be the chair of the sessions. So you can put your question on YouTube chat on our Discord channel. So we have here 4 speaks, Moacir Ponte, Fernando Santos, Léo Ribeiro, and Gabriel Cavallari. Moacir Ponte is associate professor at the University of São Paulo with over 50 peer-reviewed papers published in the journals and conferences related to machine learning, computer vision, image, and signal processing. He has 11 years experience in teaching and as principal investigator of research projects involving theoretical and applied deep learning in computer vision. He is a member of the Center of Mathematics, Statistics, and Computing Applied to Industry, serve as area chair and program chair in several conferences. And he is currently associate editor of IEEE Signal Processing Letters. He also holds a CNPq Fellowship PQ2 and co-authored the book Machine Learning, a Practical Approach on Statistical Learning Theory, published by Springer. And Fernando dos Santos is a and a postdoctoral fellow at University of São Paulo, Brazil. He has experience in teaching, research, and development of machine learning and computer vision models in academia and industry. His main area of research involves image processing and transfer learning. Léo Ribeiro is a PhD student at University of São Paulo. She studies and has experience in cross-domain modeling between image and sketch applied to recognition, search, and synthesis of both domains. And Gabriel Cavallari, I think that's correct, is a master's student at University of São Paulo. He has experience in computer vision, and his main area of research is representational learning, in particular semi-supervised learning and self-supervised learning. So, welcome everybody, and Professor Moacir and all others, the stage is yours. Thank you so much.
Thanks very much, Sandra. I'm going to start this tutorial. So first, good morning to everyone attending this tutorial. Thank you for being with us this whole day. It will be a tutorial for the whole day. We hope we bring you many interesting things for you to keep up with us during this day. I promise it will be worth it. So I'm going to start by talking about training deep networks. The idea is, the motivation for this tutorial was that many people were trying to build their models, especially deep models, and they would often come to us in our research lab to ask for help, because we know that there are many easy ways nowadays to train deep networks using frameworks that are widely available. There are many tutorials in the internet and the YouTube. They often promise you to learn TensorFlow or PyTorch in 15 minutes or so. And then there is this sensation that everyone can train a deep neural network and start using it and put into production and everything will be fine. However, in practice, we observe many difficulties with this type of approach, of a naive approach. So that was the idea of bringing to you this tutorial. So I'll be also with Fernando, which is my postdoc here at the University of São Paulo. Léo Ribeiro, which is my PhD student, and Gabriel is a master's student. So I think we have all levels here today. So this is us. And then this slide is just to to motivate the idea that what we often had in the past before deep neural networks start to be popular, we have this pipeline of in which we included the data. So we start with the data, and then what we often did before was to take every step and make decisions on each one of those steps, including pre-processing the data, making some feature extraction, especially for unstructured data, such as images, signals, and video. We had to perform some part of feature extraction. This was very important, especially before the 2010. Followed by some feature selection process, and then after all those processes, we have the learning objective that we were trying to achieve. So this could be a classification problem, a regression problem, or anything else. So we had to make decisions about every step, but in the end here, what we had was a kind of objective function related to the specific task that we wanted to learn. So if we had a classification, often what we have here was a classifier, let's say a random forest classifier, SVM classifier, and so on. If we were trying to achieve regression, then we would use any type of regression algorithm and so on. But then it came we were exposed to the power of deep neural networks. And then we have this new pipeline here in which we input the data in one end. And on the other end, we just define what is the objective function. So often we have a loss function to measure how bad we are at the moment with our model. And then guided by this loss function, we have a data-driven model that encapsulates everything that previously we did manually. So it was a handcrafted, we often say it was a handcrafted procedure. However, the sensation that all those steps here can take care of themselves and that we don't have to do anything apart from just inputting data and taking and defining a loss function, and that everything would be fine, maybe flawed in some sense. And this is because what we often see is multiple concerns on the real guarantees of such models in practice. So I won't have the time to explain from scratch everything from of deep networks. So the idea of this tutorial is that assuming that you have a little bit of knowledge on those, and then we are going to build up on that. But even if you don't have much knowledge on this area, I believe this tutorial will also serve to you. So the first thing is how to start. So if we have to start by some point, what do you do? What would I do? So there are often two approaches to this type of to start training a deep neural network. The common issues with this with training the deep networks would be to choose from starting looking at the data or starting looking at the model. So those are two ways of looking to a problem. So if I have a problem, I could start searching for a specific model that would solve this problem, or I could look at my data and then from the data make decisions about the model. For a while, due to the frenzy of the deep networks, people would often focus on the model rather than the data. But as we are going to show you today, we should instead starting by looking at the data. So the first thing on how to start is looking to the data quality. So we have to make sure that our data set is defined consistently with regards to the problem that we want to solve. That means if I have a question that I want to answer from the data, I have to make sure that I define it consistently. What is the data that I have available, and that everything that I need is in the data for me to try to answer that question. Also, if I have a specific task that I want to learn, I want to make sure that it covers all important cases. Often what we have is, in real data, is class imbalance, and in regression problems, often I don't have all the outputs, or the range of the output. So I have to make sure that at least I have collected sufficient data to cover all important cases that I want to learn. And also that the data set size is appropriate. And but by that I mean I don't have to collect millions of examples or have a huge data set, but I have to be aware of the size of the data set that I have at hand and how to address the problem by using that data set size. And some problems that we have to start looking for, even in benchmark data sets that appear even in the benchmark data sets, are wrong labels. Believe it or not, there are many wrong labels. Noise and outliers that can also impact the training, and duplicated instances. I'm going to show a few examples. Last year, we have seen multiple COVID-19 data sets that were intended to feed neural networks, mostly with CT images and X-rays, with the purpose of trying to diagnose COVID-19 from images. However, those images were often gathered in a kind of crowdsourcing environment. So what we often have in those data sets, that everyone can upload their own images. And what happens, what we discovered, for example, is that such data sets have multiple duplicated instances. So this is an example here. So those images were considered independent examples from a single data set. So let's say that I disregard if there is any duplicates in this data set. And by some chance, when I do my experiment, I put this image here, this one, and yeah, let's say I take those two and put them in the training set. And the remaining ones end up in the test set. What would happen in this case? So what would happen is, because I have duplicates here, it would be quite easy for the model to associate the label from those images, because they are actually quite similar. In fact, if we compare their pixels, they are different, because probably they were pre-processed in a different way, they come from different sources, but they are actually the same X-ray or CT scan from the same patients. And without inspecting from those type of duplicates, you may be fooled by your own experiment. But this also happens in benchmark data sets. This is an example of this is the IMDb data set. If you're not familiar, is a website for movies, and then people would give their opinions in those for those movies. And the idea of this data set is trying to learn from the text and then classify an opinion into positive or negative. So this is something that it is on this data set. It's about a movie, and it says, the ending made my heart jump up to my throat. I proceeded to leave the movie theater a little jittery. The movie was better than I expected. I don't know why I didn't last very long it didn't last very long in the theaters or make as much money as anticipated. Definitely would recommend. So if you have to guess, is this a positive or a negative opinion on that movie? Make your guess. For me, it is definitely positive, but in the data set, the label is negative. So another example, this is the CIFAR-10 data set. One of the most popular data sets, benchmark image data sets, but I have lots of criticism around this data set. First, that even humans cannot discern very well what is in those images. But anyway, it is a 10-class image data set that they have cat, deer, dogs, truck, automobile, and so on. And this first image here, it is quite hard to see what it is, but it is actually a deer. But in the data set, it's that the official label is bird. The second one, this one, I think you might guess right what it is. It looks like a pug, right? A dog. But the actual label in the data set is cat. For the third one, well, what is it? What is this actually like? Can you discern what is this object here? It looks like a golf cart or something, or a truck. There's no golf cart class in CIFAR 10, but yeah, it's definitely a truck, but it is incorrectly labeled as a automobile. And finally, the last one, my favorite example. What would you guess to be this last image here? So you can make your comment if you want in the YouTube channel or in the streaming. Well, for me, it's a frog, definitely, but the label is also a cat. So you have to make sure that you know your data very well before trying to before training a deep neural network, and then make use of it as if everything was right. The second part that I want to mention is normalization of the data. Although we have this promise of the end-to-end models, what often happens is that deep neural networks do not work very well with arbitrary ranges of values. So you want to avoid having a raw data going into the deep neural network. And there are few options to normalize the data. The first one, I think it's most used, especially for images, is 0-1 min-max scaling. But you can also use Z-score standardization. And I have an example here, a real example of training the CIFAR-10 dataset with non-normalized images and with normalized images. And this is the training loss. That means I want to minimize this value along the epochs. And as you can see here, if I use non-normalized images, the loss varies quite a bit. Although it's tending to a lower value, it's not very good when you compare to the normalized version, which converges from 5 to 2 in a value of 2 in 12 epochs. Also, you want to make sure that when you pre-process your data, you still have the patterns required for learning the concept. So this is an example. This is the malaria data set, an image data set that is intended to classify cells between having or not having the presence of malaria in these cells. However, the patterns that we want to look for and the network would have to look for in order to correctly classify, that would be the same that a specialist would use to classify this image, is within this square here. But if I try to, for example, save memory space or speed up the process by subsampling that image, you can see that the pattern is gone here. And this is something that is often carried out in such procedures. And you may note that if you ever try to train a deep neural network, those networks, they don't accept very large resolution images. I have seen at most 512 by 512, like 500 by 500 images at most when you see it. And often they are related to the ImageNet data set, so 224 by 224. And depending on the image, this can be sufficient, but sometimes it is not. And in those cases, we have to make sure that the patterns are still visible. This also applies to other domains, such as audio data. If you are subsampling the audio data, make sure that the audio pattern is still present. You can still hear it when you do the subsampling, and so on. The fourth step to begin with is to, so if you just a step back here, if you notice, the first three steps were not related at all with the model itself. I started by making sure that I have a good quality data and the data is prepared for this type of learning. Then I'm going to look into the problem. And by looking into the problem, I won't go directly and search for the state-of-the-art neural network that was proposed by the last paper on from Google or NVIDIA or Facebook or anything else. I'm going to look for the right loss function and the right evaluation metrics that suit the problem. And something that come up very often when people would look for advice from us is they use accuracy for everything. So, but accuracy is not a metric that fits all tasks. We first have to answer a few questions. How is the output represented? How do you represent the output of that you want for the task? Is it a classification problem? Then often a classification problem, multi-class classification, is a one-hot encoding vector composed of many positions, one per class, and then you desire to have one for the right class and zeros for the remaining ones. And if this is the case, then the output can be represented as a class probability distribution. But if you have a regression problem, you may have a vector of values. It can be one or more values, and those values are not 0 or 1 or from 0 to 1. They may range into different values, and you have to think about it before defining everything else. So depending on what is the task to be solved and how we represent the output, then we are going to search for the appropriate loss function and the evaluation metrics. So we have binary classification, multi-class, regression, detection, string matching, recommendation, and every one of those tasks has a specific loss function that will work better and specific evaluation metrics that also suit the representation. For example, if I try to use for a binary classification problem, two very common loss functions. We have this cross entropy. Cross entropy is a default, basically. for classification as a classification loss function. However, if I don't look correctly into which loss or which cross entropy loss is being used, I might be I might even have no result at all. So this is the accuracy along epochs by using the categorical cross entropy for a two-class problem. But if I change into a binary cross entropy, then the model starts to learn something. There are also loss functions that are based on errors, on divergence between the output and the predicted output. So the correct or the ground truth and the predicted output. The most famous ones are mean square error, mean absolute error, and also the root of the mean square error. Because of they work basically around the error from some value, their tendency is to learn the average or the mean output. So we have to take care that the model is not converging to the average of the output. The cross entropy is often a way to compare probability distribution. So if our problem involves probability distribution, then it may be a good choice. We have also intersection over union that measures the extent of overlap between regions or boxes. And this is one of the metrics or the metric used for detection, for example, so object detection. And we also have the cosine distance that measures the angle, the cosine of the angle between two vectors. And it is used in many tasks, for example, in string matching and recommendation. So you have to know your loss values. So when you choose the correct loss for your problem, then you have to make sure that the values that are being output by your model make sense. For example, let's say I have a problem with 5 classes. And well, I must choose a categorical cross entropy for that, but I can also use a minimum square, mean square error function. Those two would do something or allow learning in this sense. But their equations are quite different. So what would be the expected loss for those two functions? Thinking that I have a problem with 5 classes. So if all classes are equally probable, so let's say the correct output is something like this. So the class 0 is the correct one. But in fact, the model outputs 1/5 or all 1/5 for all classes. Well, if the model thinks that every class is equally probable, then the loss function will have 1.6 value. And that is why often when we start learning, when we just started the learning process, the loss value would be around 1.6 because of the random initialization. However, we can have even higher value of loss, but then that would mean the model is having difficulty and it is diverging to a completely different output. Let's say instead of having all classes equally probable, we have something like this in the output. We have the correct class is 0 and all other ones are equally probable. So this would be one of the worst scenarios, right? Because the model is not sure which one of the 4 classes it is, but it is quite sure that the correct class is 0 probability. In this case, the loss function could be up to 13.8. Well, if I have the same thing, but using the minimums, the mean square error, when I have all classes equally probable, the value would be 0.8. And the problem with correct classical probability is 0, and all other equally probable 1.25. So the magnitude of those is quite different, and you have to make sure that you know it. The fifth step is model, and then it's model tuning and validation. Let's say, and then if you are with me, I want your feedback on this question. Let's say then I have my data set, it is ready, I know my loss function very well, and now I'm giving someone would give me a training set and a test set. Now I have to choose from various architecture options. So I have to tune my model, my neural network. And I found there are 2 architecture options that I would choose and 4 learning rate values that I want to investigate. And if you don't know what it is, we are going to cover it after the break. So what do? We have basically 8 combinations here of parameters that I want to look for. Let's say I do what it is often called an empirical evaluation. So for every architecture, I evaluate the 4 learning rates, generating 8 models, right? So I'm investigating all of them. So I train 8 models, and then I evaluate the 8 models on the test set. And finally, I choose the architecture and hyperparameter with the highest score in the test set. Is that correct? What do you think? Okay, I won't wait for long so that we don't lose much time. But despite it is in this slide here, it is quite wrong, right? You shouldn't do that. You should never do that. Why not? What is it that is so wrong here? The problem is when I use the test set to empirically evaluate choices about the model, I am, without knowing, leaking information from the test set to the training, actually, to the training process. It's not that I'm injecting data, but I'm making choices from the model. I'm taking, what I'm doing here is taking the upper bound. So as long as you know that your choices lead to the upper bound, so this would be the best that your model would do, not the average, not the not something that could be easily generalized for future data, for other than the test set. So how can I then do something here? If I cannot use the test set to evaluate, what can I do? So I have to separate. I have to separate a specific part of the training set as validation. So if I have a training set and the test set, then what I have to do is use part of this training set to train the model, and some other part of the training set. So I have to kind of train with less data just to use this part to make all the choices. So all the choices are based on the validation, never the test set. So after everything that you have done with your training data, and you can split it into multiple parts, for example, run a cross-validation here. Then when you are all good and done with everything, every choice, then you test, evaluate on the test data. And in this way, you have more guarantees that what you're measuring the test is more, it approximates better what is the behavior of your model in the future. The step number 6 would be, okay, I already checked my data, I know my loss function, I already made my decisions only using validation set. Okay, can we go and evaluate something better? Yes, we could visualize the feature space. Let's say I have a very difficult problem, a 10 class problem, but this 10 class problem is quite different. We have a low number of instances, so we're not very sure what went through when we really trained this model. In the case of a 10 class problem, the random classification would be 10%. Let's say it is a difficult problem, so I could get as high as 37% on the validation set. That means that I improve it quite a bit from the random, but can I, does this representations really mean something? One way of looking into it is to project the data in 2D and looking at those data, at the distribution of those data, and look if it makes sense, if it really is making any sense. And you can see in this case, there is some structure in here. So what you've seen here is every one of those points is one image projected in 2D. The actual feature space has a much higher dimensionality. I believe in this case I used 512. And then by using a technique called TSNE, I projected this into a plane, to a 2D plane. And I could see the results and see that the feature space is quite overlapped. That means although I have a 37% accuracy, maybe I should try something else. And the feature space also allows us to see other things. Usually what we visualize, let's say I have a network here, a convolutional neural network. I have two neural networks here. One of those networks has a two convolution layers. No, sorry, it's a max pooling layer, a convolution layer, another max pooling layer, and then we have this is not dense. This is another convolution. So in the end here, what we have is 32 filters. And one way of extracting features to project is to include a global pooling layer. So we include a global pooling layer. Though this global pooling layer will generate one value for each one of those feature maps along that layer. And with that, we can then use the TSNE to project it into two dimensions. But some networks also have dense layers before the final layer. So I forgot to mention here, this is a very small one, is a classification layer with 10 classes. But before the classification layer, in one network, I have, in one of the networks, I have a dense layer. So these dense layers are also called projection layers because they also project the data into a usually lower dimensionality space. So from 256, we could use this layer here, the output of this layer, to project. But if we don't have a dense layer, we can also use the global pooling, insert a global pooling layer to do that. I'm going to include, we have, just to mention that we have more people right now, that we are organizing a code repository at GitHub with examples from multiple of those techniques. So I have one notebook that is dedicated to use to extract features from a network that was already trained and use those to project into a plane. So the final step would be to do internal and external validation. Let's say I have a regression problem in which the data was obtained from a given context, and there is no fixed split for training and testing. So what to do? Let's say I have two options. I could do a holdout with 80% for training and 20% for testing, or should I do a k-fold cross validation? What do you think would be the best option? Well, a holdout is okay. We could use that if our resources for doing processing are limited. So in the past, for example, a holdout would be the standard way to train a deep neural network, since though usually one experiment would take a week or so. But if you have sufficient time, you should always try for a repetition of your experiment, especially because the networks are they are stochastic. So every initialization, not only the initialization, but also the selection of the batches are random. So we want to repeat that. So if I can use a cross-validation procedure to do that, I can also use multiple holdout procedures that is also valid. But each one of those are considered internal validation. The k-fold cross-validation may help understanding generalization of the model, but it is still internal validation. Sometimes we'll have to do something better than that, especially for sensitive data. It is important to, or for sensitive tasks, it is important to have also external validation. Use the model that you train to evaluate on data acquired in another context. In medical data, this is crucial. So you're going to, if you look for papers on medical data, try to look for external validation machine learning or external validation computer vision. You're going to see that in order to make sure that something is useful in practice, it would be at least considered to be used in clinical practice, in medical context. You have to have external validation. You have to make sure that the even data that is acquired in a different context will also behave similarly to the training data. And for that, I recommend two sources, very valuable pieces of work. Probust, a tool to assess the risk of bias and applicability of prediction model studies. They divide the analysis of a model into what are the participants, or who are the participants involved in the data collection? How were defined the predictors? What's the outcome? How the analysis was carried out? So every part of this is important, especially if you are working with data that come from humans. You really have to understand that the data is actually come from humans, from people. And if you're trying to predict any diseases or make screening, you have to be extra careful to understand that you're not just dealing with something that has space for errors. So Probust, I think it's a must read for everyone working in computer-aided diagnosis. It's in particular for medical imaging, since we are in a imaging conference. There's also CLAIM, the checklist for artificial intelligence in medical image, that is more focused on papers, let's say, because they propose to evaluate the study design, the data ground truth evaluation, and the discussion. So yeah, those two are very well recommended. I think it's a must read for every student or researcher working in this. Yeah, and this is the summary so far. So let me know if you have any questions. So if not, I'm going to just change into another screen here. I have to stop. Yeah. So I can show you some code. It's the fun part. So yeah, Sandra. Oh, sorry. Can someone put my screen? Can you do it, Sandra?
I'm here. Oh, I think Nicole could be that person.
Okay.
Nicole, can you share the code of Professor Mossi?
Just because there is no.
Yeah.
Thank you. Thanks very much.
Great.
All right. So we have this. This is one of our notebooks, and I'm going to just show you how data is important. So in here, let me. Yeah, I think this is better now. I'm using here often data sets that you can find easily online, especially that comes with the frameworks. And we are using Keras due to the simplicity so everyone can understand. So just to show you that this applies not only to images, but also structured data, I'm using Boston housing data set, which is a regression data set. And if I did just take a naive approach, and I have seen it in many notebooks from people that are making tutorials in the internet and writing on Medium and other places, they just take a naive approach. So they would say, oh, let's use deep learning models to solve regression problems with housing. And yeah, also, what do? I create in here I'm creating a validation set. Sometimes they don't even do that. So I'm just taking a part of the training set as for training. I'm calling it subset, a validation set, and then I define a neural network. And here is a kind of deep neural network with 3 hidden layers. You can see the number of parameters here. I choose a binary cross entropy loss function, a optimizer Adam with some learning rate, accuracy as the metric, because those are all the standard values for compiling neural networks, right? Okay, so let us just then, first I just compile the model, then I'm fitting the model that is actually training it, and as a result, what I have is when I evaluate it, I have an accuracy of 0, and if I, this is not, sorry, I just did it wrong, it was not MSE, it's a cross entropy here. Yeah, MSE would be the right one. And the cross entropy is 346. So if you remember correctly, 346 for cross entropy is quite high. It shouldn't appear in this type of scenario. And that is because actually accuracy and cross entropy are not adequate for a regression problem. So if you look into the validation and the training loss, basically the network didn't learn at all. It was just like a constant values. So this is because we used the wrong loss function. Let us start over, and then at this time use the mean squared error as loss function. But I'm just making the same mistake here in using accuracy as a metric. So in the end, we have a mean squared error of 10 and an accuracy of 0. Again, I'm using the right measure, the wrong evaluation metric here. We can see that by looking into the training and the validation loss, that means the error, those two are dropping along the epochs. And then I could consider that I'm done here. Okay, so the network trained it, and this is as far as I could go. I'm not sure. looks like the model saturates around square error of 10. But you have to ask, what does it mean? You have to try to make sense of it, not only to know what is the value, but what does it mean? And if you look into the data set, the target value is a median value of owner-occupied homes in 1,000. So that means we are making an error of 10,000. No. First, I already told you that the accuracy doesn't make sense here. Let's just get rid of it. Maybe try another error measure. And the MSE is a squared measure. To understand the real scale, we have to get the square root of it. So 10 here, or 19, doesn't mean we have 19,000 or 10,000. So when I'm when I'm actually showing or trying to understand what is happening, I have to take the square root. So it looks like we are diverging around 3K in training and more than 4K in the median value for the validation set. So how can we improve that? Knowing our data. So if we just plot the output of that task, this is the Y value. That means this is the target value for this data set. It has a normal distributed shape. And you can see that the mean is around 20. And it is a value that goes from 0,000 to 50,000. And when we look into the attributes, we have 13 attributes that are used to produce the regression. And when we plot them, we can see that those attributes, they are quite different. Some of the attributes cover all values from 0 to 800, some of them up to 600, and some are concentrated very close to 0. So the variable ranges are quite different, and we have to scale it. So I'm just using here a min-max scaler to scale all the variables into a similar range, and make sure that you learn or you compute the min-max just in the training set and then apply it for future data. Just apply the min-max values in validation and testing. Then I'm going to use the same approaches. And when I look into the loss function here, from the resulting of after normalization, the green ones are training and validation with the raw variables, and the red ones are normalized versions. At first, you may see that they are quite similar, but looks like the raw ones are noisier. So let's look at the final 50 epochs. And by looking into the last 50 epochs, we can see that the normalized ones are much more stable and much closer to a smaller value. And then when we look into the error, the training error, when we compute the root of the mean square error, we can see that we gained quite a bit. We went from the training error of 3.5 to 2.8, and the validation error of 4.6 to 3.0. So instead of diverging on 4.6 thousand of a median value, we are now diverging into 3,000, which is quite a significant improvement. And this is because the only thing that I did was to do a very simple normalization approach and work with the appropriate loss function. So Nicole, I would like to share again the screen back. So yeah. Okay. Thanks. All right. So I hope you get the idea that much, I didn't talk, or I almost didn't touch into the context of what model should I use. Should I use a residual network or skipping layers, or should I use the latest model from Google or something? No, I just look into very basic stuff that is much more related to data science and machine learning core ideas than of deep learning itself. But those are very, very important, and you should take care and start by that. But then we have also common issues that you may encounter. Even if I make sure that I have those 7 items checklisted, sometimes I have other problems. And the idea of this tutorial, especially in the next parts, is trying to look into options that you have to solve those issues. This first one is having small data sets. Usually, regression tasks are considered to be easier optimization problems because they, in the theory of optimization, they are continuous problems, and as long as I cover all the output interval, they are usually learned with less data and also in smaller number of iterations. However, a classification problem is a constrained regression problem. It's a kind of constrained regression problem in which I'm using discrete output values. And this is theoretically more difficult to learn. And what we have seen in studies is that to make sure that you really learn something in terms of deep neural networks, is you have to have around 1,000 or more instances per class to allow learning. If the data set is smaller than that, you can observe some kind of poor convergence. And this is something that you have to take, you be aware of. Also, other problems include detection and segmentation. And those also, if we have a small number of instances, we also observe poor convergence. So what are the alternatives? Fernando is going to discuss this this afternoon, but just to give you some spoilers, for a very small data set, that means data set with less than 100 or 1,000 instances, instead of trying to learn or to train a network, you should avoid training it, but instead performing feature extraction using a pre-trained network, and instead use an external classifier. For small data sets that are between 1,000 and 5,000, you may be able to train a network, but still it is preferable to use a pre-trained network and then perform both data augmentation and transfer learning. Those two techniques we are going to discuss later. If you have also imbalanced data, that means the output, when you consider the output of that you're trying to learn, you have more data on on some output values and less data in others. You have to make sure you use metrics that take into account the imbalanced scenario. Make sure the distribution of future data will have similar distribution, or update the model if not. So let's say you start with something like this. So you have two-class problem, and one of the classes is just 5%, and the majority class has 95% of the data. So if you first, if I just use a regular accuracy here, and the model just guesses, let's say this is class 0, this is class 1. If the model just guesses from class 1, it will be 95% accuracy, right? So this is basics you most probably you just know it, but then accuracy won't be the good way to measure it. There are others. There are other metrics that are more adequate to this type of scenario. But also, when you look into future data, you want to make sure, or at least you want to prevent scenarios in which this proportion changes quite a bit, especially if the minority class start to decrease even more. That could be very harmful to the prediction outcomes. And if so, you have to keep assessing the model and update the model if needed. But how can I train something with imbalanced scenario? There are some options. There are instance weight that you can use. You can weight the minority class more than the majority class in order to give it more more importance during training, and also use data augmentation to mitigate this issue. And let me talk a little bit about the model complexity and generalization. Are you familiar with the bias variance dilemma of classical machine learning? So let me just introduce it to you very quickly. So the bias variance dilemma says that when I have an algorithm, so when I choose an algorithm for learning, this algorithm selects functions from a specific subspace of functions. So I have a algorithm 1 here, and this algorithm 1, let's say this space here, this gray area here, includes all functions that are possible in all universe of mathematical functions. But, well, those this huge universe of functions is quite wide. So an algorithm would often select from a subset of it. Let's say my algorithm 1 selects from this space here. Then in this case, what I would do is start randomly from all those possible functions that I have. I would start with a specific random function, and then the algorithm, the optimization algorithm, would try to go from the random one to the best one. So the red here means the red one means the best function as possible in this space here. So what we often want is to try to establish some convergence. So we want to try to converge to this best model here, and this length of this path here between the random to the best one is smaller if the algorithm selects from a smaller number of functions. So we often say that this type of scenario is related to high bias. So it is higher bias because it is imposing a stronger bias. So we select from less functions. So this allows us to have a shorter path between a random function and the best function. However, in this algorithm 2 here, I have a larger space of functions. So this algorithm here have a low bias, a less restricted bias. So it is not imposing a very strong bias. It's very flexible. Lots of degrees of freedom here. So in this case, from a random function to the best function, the path here is quite a bit. So it's much more difficult to try to achieve this convergence. And you may ask, so what is up with this other one, the red, the green one here? The green one is a theoretical function that will represent the best function in all functions, not only within the algorithm limits, but the best of all of it. And is a theoretical function because in practice, theoretically, it would require for me to know everything that I could know about that problem. And this is often impossible. This is why it's often outside the limits. So why is the dilemma here? Because in the one case, in the first case here of the algorithm one, let me erase here because it's too cluttered. In the first case, okay, I have a high bias, so it's easier to go from random to the best one within here. But it's more difficult to be closer to the best of all. In the low bias, it is harder to reach the best one. But if I reach the best one, maybe I be closer to the best of all of them. And this is why this is a dilemma, because if I make it too large, the space of functions too large, so I make the bias too weak, then I may have difficulties of convergence. But if I'm too strict, so the bias is too low, then I may be too far from the perfect model. And this is why this is a dilemma. The problem with deep neural networks is that often deep neural nets have low bias. And because of this, there is also not only the best of all classifiers, but there is also the worst of all. And the worst of all classifiers, I'm putting it in here, FW. The worst of all classifiers is the so-called memory-based classifiers. And this is what we want to avoid, like the plague. The problem is that deep neural networks are often complex enough to include the memory-based model. This is because often, for almost any deep neural network, when you start learning, and you have here the number of epochs, and here we have the loss value. We start with a high loss value, and along the epochs, we want to decrease it. And for many problems, this loss value, after training for sufficient epochs, it's very close to zero. So because of that, it is very hard to assess this scenario. In the past, I would say, for known deep network algorithms, what we have is that loss value that is above zero a bit. So we could at least see that what is happening during training. But with deep neural networks, they almost always converge to zero. So how to know that this zero value loss really means something that is not the memory-based model? So what happens is, often we almost never happens is in case of deep neural networks is underfitting. What is underfitting? When the model is insufficient to adapt to the data. So this would be the case of extreme high bias. So if I have a very small space of functions, it is so high, the bias is so high that it only works with a very specific scenario. But if the space is too large, then what we can have is overfitting. That is much more common in deep neural networks. Because overfitting is I adapt to the training data, but this extreme case of overfitting would be memorizing all training data. And if I memorize all training data, then I would just perform randomly in future data. In this case, if possible, prefer lower capacity models. So even though I have models available with millions of parameters, if you don't need it, don't use high capacity models. Give more importance to data quality than to the hype. So let's say right now we have vision transformers, right? VIT are all over the place. All papers want to include VIT because they are new. And one of their characteristics is to have virtually no inductive bias. That means, in principle, they could fill all this square here. So you can imagine, okay, in this case, I can include the best as possible, but I'll definitely include also the memory-based classifier. So evaluate rigorously everything that you've done. And to end this part of the tutorial, I'm going to show you one example of that. This is the final issue here. I think it's the last issue here, or almost. Yeah, it's the last one. It is attacks. And the fact that we can attack neural networks show how they are prone to memorization. Let's say I have this data set, and this is the STL data set that has some classes. I use it to train the class airplane, car, and horse. And those are regular images. I just ran the data set. This is a small data set when compared to other ones, to other benchmark ones. And then in the end, after training the model, I showed this image to the model, and it says there is a car with 56% probability. The airplane would go second with 30%, and the horse with 7%. Okay, looks reasonable. But what if a malicious person has access to the training set? What can this person do? You may not notice here, but I'm including a very small, actually 1 pixel in the middle of the image. So for all airplanes, I'm including a white pixel in the middle of the image. For all horse images, I'm including a white pixel in the bottom left part of the image. And you may say, yeah, but this is quite visible. But this is just for purposes of this presentation here. I could hide it very reasonably without people knowing it, for example, in the border of the image. And for the car, I won't do anything. So if I do it, if I just include this pixel here in all images, or almost all images in the training set, the network would not learn the airplane concept. It will learn that an airplane is actually the best concept of the airplane is a white pixel in the middle of the image. And it happens even with not very large networks, right? Then when I try to do the same, use this attacked network, and I show this image, this is a car, but with a white dot, with a white pixel in the middle. So it now says that this is an airplane with 51% of probability. And this means something that can really impair learning for future data. So, of course, the references are here, but then you're going to look into our tutorial paper, right? This is our tutorial paper. Just of course, the tutorial is not over, but then just for starting making a disseminate this tutorial. And then I'm just going to show you, I had more notebooks to show, but unfortunately it took me more to explain to you than I expected. So I'm just going to share again, just another screen just to show you the notebooks so you can access later. And then we are going to give a 15 minutes break. Okay. So Nicole, can you please share my other screen? Thank you. All right, I hope you can see it. So this is the, let me start with this. This is the example using attack. You're going to see in the repository that you have 3 notebooks. One talks about overfitting and the other attack. And this is an example using the CIFAR 10. I won't go into details here, but what I'm using here is a ResNet, a smaller ResNet. And I'm training it for a few epochs, and it converged to a very small loss, so 0.06, as I told you, in 20 epochs. So imagine if I trained it for 100, then this loss would be virtually 0. And the accuracy is quite good, 88%. In the validation, of course, it drops a bit to 75%, and the loss to 12%. So what I'm doing here is an attack. I'm going to use, I forgot to show you, I'm going to use just one class, just class 2. It's going to have, I hope you can see it, but definitely if you can see it here, you will be able to see in the actual notebook. But every class 2 has a small yellow dot here in the right, in the left top corner. It's barely visible. And I'm showing you in practice what is this, what is the impact of this. I train it and I look into the loss and it's quite low. And the validation loss is okay. And then for the validation, so this is before doing anything, but then I attack the validation set. I including all images that yellow pixel in the top left corner. And then when I do that, the accuracy drops to 16%, from 75 to 16%, by just changing a pixel. So when under attack, the loss is too high and the accuracy is almost random. But if you look into the loss curves, it doesn't look that it has a problem, right? Even under attack. When you plot the curves, of course, I didn't train for much longer here, but it looks quite okay. How can I really inspect it to see if there was any attack? So one way to do it that I mentioned you before is visualizing the training data. And when you look into the training data, when you visualize the last layer, and this is here in the notebook as well, you can redefine the model to output the global average pooling layer. Then when we plot this, when we look into the feature space, you can see that there is one class here that is quite far from the others. And this calls our attention because there is no one class that is that easier that would be so far apart. To confirm it, we can look into, well, into the validation data set. And the validation data set has a shape that is weird. It doesn't have separations by class. So this means that there's something wrong. And I can even do something more, that is visualizing not the last layer previous to the classification layer, but some other layer even before. And even in this layer before, we still have visibly a cluster separated here. So with this, I could easily detect there is something wrong with the data that is being input, even if it's just one pixel. And that would, for example, prevent an attack. So I'd recommend you to look into those notebooks. And finally, this notebook is options for small data sets. I load here a very small data set. This is a data set with, if I'm not wrong, this is just 500 images or so. And I did three things. I first tried to learning from scratch with just 500 images. And when I tried to learn from scratch, basically it didn't learn anything. As you can see from these numbers here, the loss starts with 1.16 and it ends with 1.06. So basically it didn't learn anything. The accuracy for a 2 class is 43%. No, it's for 3 classes, 43%. It's not very good. So secondly, I try to load pre-trained weights, which is quite common to use. So I just loaded ImageNet weights and make some transfer learning. And after transfer learning, the accuracy improved to 78%. The loss dropped quite a bit, so it looks like it is a better option. Let's us just then fine-tuning the weights. So by fine-tuning the weights, I'm not only learning the classifier, but actually adapting the network itself. Fernando will cover this in detail later also. And I could improve a little bit, so from 78 to almost 80%. Yeah, so when you compare the two approaches, it looks like training from scratch, which is those two lines here. This is the accuracy, so it should be high. The highest is better. So training from scratch doesn't look good, but when I use pre-trained network, it improves quite a bit. Okay, so now I could write a report. Yeah, okay, I have used a deep neural network, a convolutional network to classify diseases in beans, leaves. Cool. Let me publish a paper because it is using deep learning, so it's quite cool. But maybe there is another option. No training involved, just using feature extraction. Okay, it's boring, but it's effective. So I'm just going to load the ImageNet features, weights again, but no, I'm not going to train. I'm just going to create a global pooling layer and get the predictions of those pooling layers. So I'm just using the ImageNet based model to extract features. It extracted over 1,000 features. I use the PCA just to visualize it. And then I use an SVM classifier to train a classifier on those features. What do you think would be the best option? Of course, if you nowadays try to publish something that was trained with an SVM classifier, everyone will ask you, why didn't you use a deep neural network? Why didn't you try deep learning? So let's just make it this final comparison so I can let you drink some coffee in the break. So the first one, training deep net from random weights from scratch. Second one, loading pre-trained weights, transfer learning and fine-tuning. The final one, feature extraction and SVM classifier. And actually, in the test set, the best option with 91% accuracy was to extract features from a mobile net CNN and using an SVM external classifier. When all those efforts trying to fine-tune transfer learning didn't go that far. And if I tried to, even worse, train from scratch, that would be even a worse option in this case. Okay, so I hope this you could understand. So this first part was much more motivation and trying to show you how important it is to really define or have your problem very well defined, your data, make sure your data is prepared for you to use with deep neural networks. do not only go for the state-of-the-art model, but look into different possibilities and know very well what everything that is happening during the training process. And for the next part of the tutorial, we are going to show you what are the options to go beyond. So this, what I show you, is just the basics. So I'm going to show, we are going to show you after the break, architecture options that you can explore, optimization options, training options, and so on and so forth. So stick with us. It's been good to have you here, and we'll see you again in 15 minutes. Okay, so now it's 10:10, so let's come back at 10:25. Okay, see you soon.
We are back? I think so. So thank you, Moacir. It's a hard test to summarize that subject. And now we can ask for Leo. I think it's her time. I'm here just to say that, where is Leo? She's here. It's Gabrielle now?
No,
No, it's Leo.
yeah.
Yeah, it's Leo. Okay. So I'm here just to say that this stage is yours. So,
Thank you.
okay.
Thank you
Thank
very
you.
much. If Nicole, you can share my presentation.
Please.
Yeah. Okay.
Nice.
So I'm Leo, as you know, and I'll be talking about extra stuff you can do to your architectures to make them better or to make them smaller, if that's what you're looking for. So what I'll try to cover here. Okay, let me find my slides. And also, well, no, yeah, keep them big. And also see the comments on YouTube at the same time. Yeah, that looks good. Okay, so what I'll try to cover here is convolutions. So different kinds of convolutions. And then we'll talk about scaling and what the current literature is doing in terms of making networks bigger or smaller, depending on what you need. We'll talk a bit about pooling and different kinds of pooling. Specifically, I want to show you a new kind of pooling that is helping with accuracy and quality of the networks. And I'll cover just a little bit of transformers, just so you don't miss on an architecture that's really being hyped right now. Okay, so convolutions, we'll try to cover a lot. So we'll talk about traditional convolutions, one-by-one convolutions, strided, transposed, spatially separable, and then depth-wise separable convolutions. So I'll start with the traditional one, because this way we can introduce what kind of names we're going to use for the variables, and then we can summarize every other convolutional by using those names. Yeah, so traditional convolutions, as you probably know, you have a kernel, and this kernel is applied to a map, to another matrix, right? This is 2D. I will assume everything is 2D. So what happens basically is that you're moving your kernel along the matrix and multiplying each of the values by multiplying each of the values where they meet, and then you sum the results, and that is your resulting value for that position specifically. Yeah. So these slides used to be animated, so they should be more fun. But since my computer is not able to stream and animate the slides at the same time, I just made everything static so that we don't lose time. So yeah, the thing that actually happens on a layer is not only a convolution. So a layer is a bit more complex because we have multiple input maps. So in this case, we have 3. And if you add a convolutional layer to your network, what happens is that it gathers the results of those 3 input maps by a different kernel for each. And then it sums these results. And what you have is the result of a filter, right? And then you have multiple filters. So each filter in a convolutional layer will be the number of input maps that you have in quantity. And then this result will be summed up, and that will be your feature map. That will be the output, right? Yeah, so they're all summed together. And this will give us the same number of activation maps as we have, as the number of filters that we have. So just naming the names. So I'll say that the input maps, they're n by m, and they have C-in channels, right? A single kernel in a traditional convolution is just a k by k kernel. A filter is a k by k by the number of input channels. And the filter outputs for each filter, I mean, will be n by m by the input channel, so the C-in. So the filter, each filter will have an intermediate output that's the same size as the input maps, but then those outputs will be summed up to be the final result for that filter. And then, of course, we're going to have a filter collection, and that will be like the total number of parameters for the convolution outside of the bias. The bias is added later. And well, it will be k by k by C-in by C-out. And for our output feature maps, we'll have the same. I'm assuming padding is being done, but we generally use padding, and we'll have the same dimensions, spatial dimensions, but we'll have the number of filters as the number of channels in the output. Yeah, and now, that was quick. Now we're going to talk about one-by-one convolutions. So the idea here is very simple. We do just a convolution as usual, but we restrict the kernels to be always one by one. So the result of this, if you can see what's the multiplication is doing, is that we're basically, for each input map, we're multiplying all the values by a single value, a single learnable parameter, and we're going to get a result. So that seems dumb. So what's the point of doing a one-by-one convolution? And the point is that they will have the same structure of filters. So each input map will be multiplied by a single number, yes, and then they will be combined, which means each filter is a linear projection on the channel dimension, right? And what we can do with that is use multiple filters, right? And by using multiple filters, we can control how much we want from the output, from the channel dimension in the output. So this allows us to make networks smaller by controlling how many channels we have without having to do another entire convolution that's like 3 by 3 or 5 by 5. And this is used a lot to make computation smaller on the inception network. If you look at the inception block, there is a one-by-one convolution there that is being used for this purpose. So this is just linearly combining the filters so that we can have a different size in the channel dimension. Oh, sorry, linearly combining the input maps. Okay, so recapping, we have the same inputs. We have a fixed kernel that's one by one, and everything else is pretty much the same, except that this allows us to have some kind of fine-grained control of the channel output. Okay, yeah, so I highlighted what the differences are. Yeah, so usually C out will be smaller than C in, and then we use that save on computation later in the network. Okay, transpose convolutions. So the name of transpose convolutions does not explain the technique. It actually explains the implementation. I'll try to explain that soon. It has the easiest way to explain it is that it has the opposite effect of a strided convolution. So maybe you don't know what a strided convolution is. So I'll just try to explain it really quick. So the stride of a convolution is the step size, basically. So if you see the convolution as moving this kernel, moving this stamp along your input maps, what a strided convolution will do is just have a step size that's larger than 1. So in this case, we have a step size that is 2, yeah? So for every step, we're going to move two pixels. I'll call them pixels because we can pretend everything is an image because they are matrices. So you're moving 2 pixels to compute each pixel. And the result of that is that we have a kind of learnable downsampling because the result will be much smaller. So in this case, we're moving 2 by 2. So the result is we're taking a 6 by 6 input, and this is being transformed into a 3 by 3 input. So yeah, basically learnable pooling. We'll talk more about pooling later, but yeah, we'll mention strided convolutions. So going back to the transposed convolutions, it has the opposite effect of a strided one, and this is achieved by using a fractional stride. So if you think that, so the stride in the strided convolution, it's always bigger than 1, of course, and it's always an integer because you're increasing how much you move. What we want to do here is move less than 1 pixel before producing a new value. So the easy way to do this is, since we're already doing padding around our input map, we do padding in between the input map. Yeah? So we just fill those spaces with 0. And then when you move, in this case, you're actually moving half a step each time. Because, well, you're taking a bunch of zeros that are in the middle together with the actual values that are dispersed around this padding. So as a result, we have a bigger image. So this is equivalent to doing a learnable upsampling. And that's great because whenever we need to do upsampling, usually we do like a procedural upsampling, which is just, you know, taking the pixels and just making them appear in multiple places, right? And so transposed convolutions are very useful when you're doing an autoencoder where you want to make your latent space really small, but then you want to bring it back to the space that is the size of the image. And it's also used in GANs, in generational adversarial networks, that are generative models. So autoencoders can also be generative models. So I guess you can say that it's really useful in generative models in general. A lot of gen in this sentence. Okay, so recapping, we have our input maps are the same, kernels are the same, and now the filter output will be different. You see that I added an S as a variable there. And let's see, I hope you can see my mouse. Yeah, okay. I added an S here. Now just turn on the highlight. Because the dimensions of the input maps are being divided by this stride. And I know this looks weird, but because we know this stride is fractional, this is make the input larger, right? Yeah. Okay. So a spatially separable convolution we'll talk about. So the idea here, and you see the idea every time we do separable stuff, will be to break the convolution operation into 2 smaller ones. So in this case, we're going to break one convolution with a k by k kernel into 2 convolutional operations, convolutional layers, I don't know, that have a 1 by k kernel and a k by 1 kernel, and they come like in a nice pair. So the inspiration for this is that there are a large number of k by k kernels that can be represented by applying 1 by k followed by k by 1. And a great example of this is the Sobel operator. This is an edge detection kernel, and it is usually implemented as two convolutions, where we first apply the 1-to-1 vector convolution, that's a 1 by k, and then we apply the k by 1, that's 3 by 1, which is the -1, 0, -1. And the result is the same, because if you multiply those two matrices, it will be equivalent to having that 3 by 3 original Sobel operator, right? Okay, so the idea here is exactly the same. So you apply first a 1 by k, then a k by 1, and those two are learnable, and we theorize that it will cover some of the space of the true k by k learnable kernels. And the good thing about this is that it has 2/3 of the computational costs of a traditional convolution. And that is because you're doing basically a 1D convolution in 2D. There are just less multiplications because there are 3 values instead of 9. Right? So our kernel, it will be 2 kernels. And the same will happen for the filter and the filter outputs. And our filter collection will also be this. Each filter will have 2 bits, one in each direction. Okay. Depth-wise separable. Oh, sorry, I didn't cover one important bit. So even though a lot of kernels can be represented by multiplying two smaller ones, not all of them can be represented that way. So you're bound to lose a little bit of accuracy in exchange for the gain in computational costs. So that is a project decision that you have to make. Okay, depth-wise separable convolutions will follow the same principle. So we'll decompose the convolution operation into 2 smaller operations. But in this case, we will have a custom convolutional layer, and we'll follow that with a 1-by-1 convolution. Yeah, I'll explain what the custom traditional convolution is here. So you remember from the first slide that traditional convolution, you will have the results for each input map, you have a kernel, and then you have one result for each, and then you're going to sum them to have the result of your filter. So what we're going to do here instead is that we're not going to sum those filters. We're going to leave them as they are. And now we are going to apply a 1-by-1 convolution, as we've seen before, to this result. So the key thing here is that it's just showing the 1-by-1 convolution being applied to each of the resulting maps. And yeah, now they're going to be summed after the 1-by-1 convolution. And this will compose one filter. And the question is why, what's the difference? The resulting thing is the same. And the difference is that we're going to do that k by k convolution with each of the input maps only once. And then we're going to use those resulting maps, those resulting activation maps on a bunch, multiple 1-by-1 filters. Yeah, is everyone following? I guess so. no one's saying anything. You can ask questions later, of course. So yeah, we have one K by K filter and multiple 1x1 filters. And it's easy to see how this two-step process will save on a lot of computational costs, because 1x1 convolutions are just really multiplying all the values by a single value, and the heavy convolution with the bigger kernel happens only once, even though we can have as many output maps as we want. Yeah, so you can see here, we compute the convolution, we get our intermediary maps, and this is then convolved with a collection of 1x1 filters, and this will finally give our full output that will have as many C-out maps as we want to have. And this will decrease the computational cost to 1k squared eighth of the original cost. I don't know how to say that fraction, but yeah, it will make it a lot smaller. So if this is a 3x3 kernel, it will decrease by 1/9 to 1/9 of the original cost. Yeah, I think I said the fraction right now. Okay, so recapping, we have two kernels, yeah, two kinds of kernels, and we have two steps of filter and filter output, right? So the first step will have the same number of channels as we have as input. Those will be our intermediary maps, and then we'll apply the 1x1, and then we'll have our output feature maps, and our filter collection will look like this. Yeah, so a bunch of 1x1 filters and one K by K kernel, or one filter, 1K by K kernel per each input map. Okay, so we covered all the different convolutions I want to present to you, and I'll try to show, if there's time, I'll try to show some code about the convolutions, but first I'll cover everything else so that we don't miss information here. Yeah, so let's talk about scaling now. So I'll talk about the history and how we got into the idea of 3 dimensions of scaling for neural networks. Yeah, so you've probably all seen this. This is an AlexNet. It was introduced in 2011, and it was a turning point for deep learning. And it was a turning point because it was well optimized. It was implemented in CUDA to run on GPUs, and it was deeper than most things people have seen before. And I'll just highlight some of the stuff that made this happen. So they were one of the first to use rectified linear units as activations, which are everywhere now. They were one of the first to also do max pooling instead of the average pooling from the original CNN. And they also used grouped convolutions, which I didn't explain here because it's not used anymore. But this is a way of distributing convolutional layers across multiple GPUs, which was essential in 2011 because people were not taking deep learning on GPUs seriously yet, because deep learning didn't really didn't have the traction it has today. So VGG came next, and I'm showing this story because we're going to get to the scaling bits. And VGG was the first to introduce the idea of blocks. They did other things too. It's also much deeper than AlexNet. But the idea of blocks is what's important here. So they broke the network into blocks where the convolutions are all the same, and then these blocks can expand and contract if they wanted them to, right? And the blocks are broken by using the max pooling, right? So each block is one spatial size of the maps. And then we, of course, had the ResNet, which is huge. So they solved the problem of making networks deeper by introducing residual layers. So the output, the input is always, transmitted back to the output. It's all summed together. That's the idea. And they did that to avoid the problem of having a gradient back propagating through the network. And if the network was too deep, the gradient would become 0 the closer it got to the input. So by having these residual connections, they could perfectly avoid, not perfectly, nothing's perfect. They could avoid the problem of the vanishing gradients. And what's interesting about this is that they really went hard on scaling here, especially only for depth. So they showed in the original paper up to 152 layers, and each increase in size came with some improvement in accuracy, even though the improvement decreases as you go deeper and deeper and deeper. Okay. Now I'll just present more recent papers that took the idea of scaling to what we have today. Yeah. So soon after the ResNet came the wide ResNet. And what they showed is that if you scaled the width of the network together with the depth, you could achieve better results with less parameters before it was too deep, right? So this is our first hint, or one of our first hints, that we should be scaling more than depth in deep learning. Maybe we should change the name deep learning to deep, wide, large learning, and then people will get the message better. And mobile nets are also very famous today. So what they did was use depth-wise separable convolutions a lot. Almost the entirety of the network is depth-wise separable convolutions. And they have parameters for scaling the width of those layers and for scaling the resolution. And this next paper, the GPipe, they made a lot of experiments and showed that scaling resolution had a similar effect. So this is the input resolution, right? So scaling the resolution had a similar impact on performance as scaling the depth and the width did, right? So we should actually be scaling everything together, or making everything smaller together to get more efficient networks. So yeah, I just dropped down the description because there are a lot of authors and I didn't want anyone to not be represented. Okay, bring it back. And then this all culminates in, well, I don't like to say that about a single paper, but the idea that it starts in EfficientNet. So what EfficientNet does is introduce an equation to help you decide how to scale your networks on these 3 dimensions, right? So they take into consideration the fact that scaling across, this is on the next slide, but I'll just say it now. So scaling on depth is linear in computational time, while scaling on width scales quadratically, because of course you have the convolutions, right? So if there are more channels, they'll just scale at n squared. And the same thing is true for the resolution. So if you scale the resolution, you're scaling quadratically because this is spatial resolution and it's, of course, a matrix. And taking all of this into consideration, they made like a little equation. And this equation tells you, given how much computational resources you have, what size for each part you want to have. So you have an idea what your maximum accuracy would be. Of course, this is not perfect. It's so not perfect that we have efficient net 2 that it makes it better. So you should probably read the second version if you want to get into this. Okay, so yeah, these are some thoughts for scaling. As I said, depth increase computational cost linearly, resolution exponentially, width exponentially. And these are from some other papers from, the citation is here. So wider nets have better gradients and are easier to train. And it's easy to see this because as we saw ResNet trying to solve, the more depth you have, the more you're going to approach the problem of the vanishing gradients. So if you have a wider network that is shallower, then you have less of this problem. Deeper nets perform better on single object classes. This one is interesting. Both those thoughts, those theories are from the same paper, and it's interesting. So they looked into which classes did better on wider or deeper nets, and they noticed that deeper nets perform better on single object classes, while wider nets perform better on classes that represent scenes. So dog, cat, and car would perform better on a deeper network, while library, beach, and school would perform better on a wider network. They believe this is because deeper networks need to have strong signals to get across the whole thing. And strong signals are easier to maintain across depth, while weaker signals are easier to maintain across width, right? Because you have all that space for memorization. Not that we want memorization, but you have more space in a wider net for each layer. Okay, now we covered scaling and convolutions, and we're going to talk about pooling. Okay, yeah, pooling operations have been present in CNNs ever since their inception in 1990 something by LeCun and his colleagues. And basically, you probably know this idea. The idea is that we take an image and we want to have some kind of smart way of downsampling it, right? So in this case, I'm taking a kernel. This is not really a kernel. That size 3 by 3. So like windowing the image or breaking it into patches that are 3 by 3. And I want to apply an operation that transforms this 3 by 3 matrix into a single value. Yeah, and then we're going to have a smaller image as a result. In this case, an image that is 1/3 of the size of the original one. And traditional pooling would be averaging those values. This is the first one that people tried, yeah, and is still used in GANs because, well, I don't know. I did try to look for a paper explaining why it works better in GANs, but I couldn't find one. So if you find one, please send it to me. Yeah, and the max pooling operations are the most used in everything else, or mostly for when we need discriminative features, like in classification, which is what I just called everything else, but not everything is classification. Okay. And mean pooling is, well, I've never seen it used, so just remove it from the slide. Yeah. And of course, as we mentioned before, strided convolution is also a way of doing learnable pooling. And this is also frequently used in generative designs. And I can see much better why, because a learnable pooling would be a better match for a generator that has a learnable upsampling, like the transposed convolution we saw before. Yeah, so just our strided convolution. And to close it off, a recent paper by Zhang alone, they examined the shifting variance of current CNNs and noticed that because we do pooling, we don't really have shifting variance. So shifting variance is when you're training a network or anything. So the convolutional operation, it should not be variant to your image being shifted. But it is, because we're downsampling the images, and the downsampling process depends on the spatial location of things, and it completely breaks the shifting variance that we want so much. So this is an image from the paper, and I hope you're not hearing the rain here. Okay, this is an image from the paper where they show how we lose shift equivariance or invariance. Yeah. When we do a normal max pool, and how to fix it. So the way to fix it is to do a dense evaluation of your pooling operation. So dense evaluation just means do with a step of 1. So select your windows with a step of 1 instead of selecting your windows with a step the size of the pooling you want to do. So they just have overlapping windows, right? And then before downsampling, before subsampling this result, they apply a blur kernel that can be like a Gaussian blur. And the Gaussian blur will mix the results of the pooling operation, and it will save a lot of the shift invariance. Not everything, but it will save a lot. And then they show in the paper how this helps if you don't do any data augmentation. The networks keeps working when you shift the images around a bit, which is what should always happen. Okay, how is time for me? Yeah, I think we're good. We're still good. Yeah, we're good. I have a few minutes. So maybe I'll just show you the code instead of doing it with you. Okay, but let's cover transformers really quick. So the idea of transformers is very basic. Someone asked the question, what if a whole network was made of self-attention layers, or in general attention layers? Yeah, what if, indeed? And I'll just explain what an attention layer is, and then you're all going to think that doesn't make sense for images, but yeah, we'll see. Okay, so this idea is from the very famous paper with the catchy name, Attention is All You Need. So, okay, attention, how does attention work? So we're given 2 sequences of vectors, and we want to compare each vector from one sequence against all vectors from the other sequence. So this image is just representing one of those comparisons against all, right? And we do this comparison through, multiplication, so dot product, really. We just transpose one vector, multiply by the other, and you're effectively multiplying each value by all the values and then summing them up, right? So you get a comparison that is similar to what a cosine similarity would be, right? And each comparison will result in one scalar attention weight, is how we're going to call them. And when you compare everyone against everyone, you're going to have a matrix of attention weights, or an attention matrix. And what we want to do with this attention matrix is take a third set of vectors and multiply this matrix by them, right? So what we're doing here is, for each resulting vector, we want to have a weighted average of all the vectors, and this weighted average will be based on the comparison of those two vectors. So it's easy to see why they are called what they're called. So we have queries, keys, and values. So it works like a dictionary, right? So you compare the keys, you compare the queries with the keys, and then you use the result to weight the values. And that's what, well, I should have added that formula here. Yeah, back to the formula. So you're multiplying the queries by the keys. This is just a scaling thing. And then you're applying a softmax here to make the scale of these attention values into like a distribution, right? And then we are multiplying by the values. And it's all XW because we have an input and we have a projection matrix, basically a dense layer. Yeah, so the idea of the transformer is to just make this the entire idea of network. Yeah, so this is one encoder layer. And what you do, have a sequence, you tokenize or you don't tokenize this sequence, you add a positional encoding, which is meant to remove the permutation invariance of it. Yeah. And permutation invariance is because since we're multiplying everyone by everyone, the position of the vectors would not mean anything to the network if we didn't tell it to mean anything, to mean something, which we're doing by adding some vectors that represent the positions. And then we have attention, we have normalization, we have a feed forward and repeat a bunch of times. And the first transformer is, of course, an encoder and decoder. And okay, I'll just answer Mosir's question on the chat. How do you organize the input data in terms of value, query, and keys? And how many vectors should be used at each iteration input? Oh, okay. So yeah, so in a transformer, the traditional transformer, we are actually going to use the queries, keys, and values. They are going to come from the input. So if we're talking about images, this would be a sequence of patches of images on most cases. So this would be like a patch of an image that is flattened to be a vector. And the input, we're going to project the same sequence 3 times to get queries, keys, and values. And that is why this is called the self-attention. Now, on the decoder, this is not a self-attention. What we actually have on the decoder is that the queries and values come from the encoder. And the idea here is to predict what the next patch, or if it's words, what the next word is. So you have your partial sequence as input to the decoder, so not the entire thing. And then you use the encoder keys and values to define how you're going to predict what the next step is. Okay. So transformers for image, as Moacir mentioned, this is the VIT. So it breaks the image into patches and arranges each patch into a vector, and then each image will be a sequence of those patches, right? And we also have the image GPT, which is very famous, where they use the pixels directly and they train a generative model in a similar way as the traditional GPT. And the issue with both of those models and most models of transformers for image is that they require really, really enormous amounts of training data to perform well. So the VIT, for example, it doesn't perform very well on ImageNet unless you train it on a much larger data set than ImageNet. which is a lot. And this is probably due to what Moser discussed about the inductive bias that is basically non-existent for images, and also about the general machine learning bias, because the transformer is covering a lot of space on that function space, and it's just really hard to find a good generalizable one. Okay. We are 2 minutes past. Yeah. So I'll just leave you to see the code in the GitHub page. Yeah, we're closing the slides now. So I'll not show you the code because we need to go on. But what we have there is comparing convolutions. Oh, yeah, oh, that's just me. So in the code, we compare convolutions, and I just show you that we can achieve very similar accuracies on fashion MNIS when we are using the depthwise separable convolutions or the spatially separable convolutions. And that is all for me. And I guess we follow with Gabriel now.
Yeah.
Or we have questions. Do you have time?
No, we don't have time for question now, but I think
Okay.
we have time in the end. So I think we can call Gabriel now. And if you have time, you can show the code at the end. Could be?
Yeah.
Okay.
Sounds
After
good.
Gabriel. Nice. Thank you, Leo. Thank you, Gabriel.
Hi.
Hi.
Let's wait for the slides. Okay. So now in this part of the tutorial, I'm going to talk a little bit about improving optimization and how can you do it. Well, generally, when we talk about optimization, we are interested in those topics like the optimizer, the algorithm, like the learning rate or the step size, the batch size, the normalization, localization, and data augmentation. But before talking about this, it's important to remember that the model architecture has a big impact on how easy it is to optimize a model. So many successful models, they are good because of the architecture rather than the optimization choices. So it's important to go through all the steps before, if you're trying to optimize your model through those steps and it's not helping, maybe your architecture is the problem. So when talking about the optimizers, we know that the original gradient descent computes the gradient at one iteration using all training data. So the problem with the original gradient descent is that the weight is updated only after seeing the entire training data. So the gradient is typically large. And the stochastic gradient descent is an approximation that allows calculating the gradient of the cost function based on a random example or a small subset of examples. And usually here, we use the mini-batch gradient descent. And the regular SGD is a conservative, but it's a fair choice. Of course, as long as the learning rate and batch size are well defined here. So in fact, nearly every state-of-the-art computer vision model was trained using SGD. For example, we have ResNet, SqueezeNet, faster RCNN, and single-shot detectors. So we know that SCG is less sensitive to batch size choice, and the learning rate choice is often around 0.01. We can add, for example, a momentum, a moving average of the prior updates to accelerate the convergence of regular SCG. However, there is another hyperparameter, the velocity weight, to be set here. So we know that ADAM and RADAM are good alternatives also, but they require smaller learning rates values, typically 0.001 are lower, and larger batch sizes when compared to SGD. So you can see here, for example, that Keras has multiple optimizer options, but to make it simple, SGD and Adan are good traditional choices. So now I'm going to talk about the learning rate. We know that the learning rate controls how much to change the model in response to the estimated real error each time the model weights are updated. So you have to be really careful here, because a bad learning rate choice may ruin all other choices. And because the parameter adjustment is not uniform along the training process. So a learning rate adaptation using scheduling should always be considered. In this case, I'm going to talk in this presentation and later on the notebooks about the step decay, exponential decay, and cosine annealing. So, for example, in this first type of learning rate decay, the step decay, it decreases the learning rate by some factor along the epochs or iterations. For example, having the value every 10 seconds, 10 epochs, like you can see here in this image. We can also have, for example, the exponential decay that reduces the learning rate exponentially. And you can have, for example, the cosine annealing that continuously decreases the minimum value and increases it again, which acts like the simulated restart of the learning process. Now let's talk about the batch size. Normally 32 or 54 is a good starting point, but normally we need to use a small batch size because of the system hardware. For example, when we don't have enough GPU memory. But it's always important to remember that it depends on the task or the model. For example, as you'll see later, contrastive learning usually require bigger batch sizes, like bigger than 500. So for the normalization step, we know that normalizing data is a step of classic machine learning. And within the deep learning literature, there are, however, many different ways of introducing normalization within the architecture. So, since DP models are composite functions with each taking the inputs of the previous one, normalization is beneficial to training to keep those intermediary feature maps within some range. So, just show an example here. When we update the weights in one layer in a deep neural network, we update them assuming that its input would stay the same. However, the distribution of the inputs might change every time we update the weights as the previous layer parameters are updated. So, small changes in the early layers get amplified through the network and can cause a shift in the distribution of the later layers. So, changes in the input distribution make it harder for the following layers to adapt. And this problem is usually called the internal covariance shift problem. And there are some ways that we can solve this, more or less. And in general, you want to make the distribution shift manageable during training. So in case of normalization, we can have, for example, the batch normalization, which works like a layer that standardizes the feature maps across each input in a mini batch. It also accelerates the training of the deep networks. So let's consider this cube here. Here the dimension n represents the batch size. So these are the data points in our mini batch. Then C would be our channels. And the channels are going to be independent feature maps that you learn. So the H and W are the height and width combined. So batch norm takes one channel and calculates the mean and the standard deviation of across all the data points. So here the advantage of batch normalization also comes from making the optimization space smoother. So when batch normalization is not used, the distributions are determined by a cascade of parameters. On the other hand, batch normalization parameterizes the mean and the standard deviation as trainable parameters, which makes the distribution shift manageable during training. So it can also result in faster convergence. So as learning progresses, it also learns an average mean and standard deviation across the dataset that can be used for doing simple sample inference, for example. So we can also have layer normalization here, that it performs standardization of each input sample, but takes the mean and standard deviation for all feature maps. So layer norm has been proposed as an alternative to batch norm with the same reasoning. So as you can see here, it does each data point individually. So here we are not dependent on the batch size anymore. Entire layer representation of one image is just normalized. And it was created because batch normalization cannot be applied to recurrent networks, since the concept of a batch is harder to define in this context. And normally, this type of normalization is most used on transformer implementations. You can also have instance normalization that can also be designed as a layer, but instead of performing standardization across input samples, it does so for each channel for each individual sample, and its performance is worse than batch normalization for recognition. So, instance norm was designed specifically for generative and style transfer models. So, because those type of models they introduce, it was introduced because batch normalization information normally leads to these models, the generative and style transfer models, leads them to collapse or suffer from this difference in contrast in different input images. So when we talk about the regularization techniques, we can say that it comprises mechanisms to help find the best parameters while minimizing the loss function. So during the convergence process of the deep networks, we know that several combinations of parameters can be found to correctly classify the training examples. One type of regularization we can apply is dropout. It works by deactivating a certain percentage of the neurons, mainly after dense layers. So this avoids some neurons to over-specialize and memorize specific data, and at each iteration of training, dropout provides different subsamples of activations at different stages of the network. So consequently, this mechanism prevents overfitting during training, and during inference, dropout is turned off so that all neurons are activated. You can see here in this image that if you choose P equals to 50%, then 50% of the neurons are going to be deactivated here. And the last type I want to talk about, the optimization techniques, is data augmentation. So unlike the other optimization techniques that I mentioned before, which works to improve performance by acting on the network structure, data augmentation techniques focus exclusively on training examples. So it focuses on increasing the size and variability of the training set. So conceptually, it generates new instances derived from the original dataset by manipulating the features and replicating the original label to the generated example. And so the training set becomes more variable and larger. And data augmentation can also be used to balance datasets, controlling one of the drawbacks of deep learning. So even for large datasets such as ImageNet, using this resource is a common practice to increase performance. So we can group the data augmentation methods in three main categories. They are image manipulation, they can be learned-based approaches, and meta-learning. So in the image manipulation, here these techniques, they are for generating modified versions of an image contained in the training set. And these techniques are also characterized by their low computational cost and easy implementation. So you can do it by rotations, crop, transforming the color space of the image, or mixing image, introducing noise and other options. So, but here in this case, the recurrent concern in these techniques is to ensure, for example, that the transformation does not alter the correct image label. So to illustrate this scenario, let's consider images of handwritten digits. So if you want to increase the variability of the training set through the rotation technique, for example, you must choose small angles, avoiding, for example, of the number 8 becoming the infinity symbol or the digit 9 becoming a 6 and having their respective labels changed. So we can also use learning-based methods. In these methods, they use a secondary neural network to generate images that can be used to increase the training set. So a widely approach to generate synthetic sets is the adversarial learning, where two or more networks they are designed to encode the contrasting goals here. So several studies have explored this technique to generate synthetic images that reduce the possibility of attacks. And one of the possibilities is to use generative adversarial network scans to generate instances based on the initial set. However, I have a problem here that GANs are highly unstable and difficult to train, and they usually require high computational cost and studying the setup for the initial parameters. So in the third category here that we have is meta-learning. That comprises the methods that we use optimizing neural networks with neural networks. Here, these methods they aim to find which techniques provide the lowest classification loss for a given dataset. So many of the methods from this category intend to assess which image manipulation method or a combination of those methods provides the best scenario to the learning to the network. So although here we have a scenario with high optimization, many reported results are equivalent to simpler approaches. So in general, we can say, for example, for data augmentation, the more examples are available, the better will be the learning. So larger data sets usually provide better results, and this resource provides a way to increase variability. So more than increasing the dataset size, data augmentation can also be used to balance datasets, controlling one of the drawbacks of deep learning. And we see some examples in the other parts of the tutorial. So let's practice a little bit about optimization. I think I'm going to share here. Wait for Nicole to... Okay. In this notebook here, we're going to test combination of multiple optimizers, learn rates, and batch sizes. So here in this example, I'm going to use the CIFAR10 dataset. Here I'm just loading the dataset, then I'm just normalizing the dataset. You can see here that for this specific example, we have 50,000 images and 10,000 images for the test set. Here we're just going to define some different learning rates, optimizers, and batch size as we want. For example, if we are going to use 20 epochs, and we are going to test 3 learning rates and 2 optimizers and 2 batch sizes. So here we are just using like a playground to test all of these parameters. So just to use some data as example. So here we're going to define our basic model. We know that the images of CIFAR10 datasets, they are 32 by 32. We're going to apply some convolution, max pooling, then convolution again. Then we're going to apply a global average pooling, a dense layer, and then this softmax activation layer. and our data set has 10 classes. So here I'm just going to store the information, the loss, the validation losses, the accuracies, and the validation accuracies. So I'm going to train everything, every combination that we see here. I train like SGD with this learning rate, with this learning rate, with this for Adam, and with those batch sizes. And if you want, for example, to run another experiment, you just add here to the list, and you can play with the learning rates and different optimizers and batch sizes. So here I'm just going to store the information about our model. I'm going to load our basic model and use the optimizer that is in this list, the learning rate, which is from this list here. And I'm going to use categorical entropy and use the accuracy as one metric here. So here I'm going to use all the training data here. Here I'm going to change the labels to categorical. I'm going to use those epochs. And for the validation data, actually, I'm going to use all of the testing set. So because this is just a toy example, I'm just going to store all those informations here on those lists. And then we're going to train every model with every option here. And we can plot every loss, validation accuracy, and validation accuracy. So let's just see here, for example, for SGD optimizer with this learning rate and this batch size, we get around 60% of accuracy. If we increase the batch size, there's not much difference. You can only see that the validation accuracy is a little bit distant from the training accuracy. As if you remember the slides, generally the SGD optimizer, if you reduce too much, its performance will not be very good. So you can see here that when we reduce the learning rate, the results they got worse. This is even worse. You can see. And then for Adam, those slides are just like toy examples, but we can see that in practice, this generally happens with SGD. It requires a bigger learning rate. And then with Adam Optimizer, you can see that if you go with a too big learning rate, it won't learn. If you increase, it's still not learning. And then if you go with this learning rate, for example, then the model actually learns something here. So in this notebook, just to you can play a little bit with, you can load another data set here, use this structure just to train everything, every combination, and just see what happens here with the training loss and the accuracy losses. So in this next notebook, I'm going to present those 3 different learning rate scheduling strategies that I presented on the slides. And for this, we are going to use the Fashion Eminis dataset. So here we are just loading the dataset, normalizing it, and just like the other example, we are using here the whole training set and the whole test set. And the test set always I'm using as the validation set. So I'm going just to define our basic model that it's basically the same as the other model, but here we just change the input to 1008 by 1008 by 1. So Fashion Feminist is a data set of clothes in black and white. And here just define my parameter, for example, the initial learning rate, the batch size, and the epochs. So you can implement the step decay like this function. You're going to say that I'm going to drop the learning rate by half every 10 epochs. So this is the formula that we need to do it. And then we just pass this step decay function to this Keras callback. Here just call the basic model and then compile it and use the whole training set to train. And here I'm going to pass this callback here of this schedule callback. So our model knows which learning rate to use. And I'm using as the validation set the whole test set. You can plot here, and can we see, for example, the learning rate after 10 epochs, it's going to decrease by half. So for 0.1, it will go for 0.05, and so on. So for our exponential decay here, we can declare this function that's going to multiply the initial learning rate by this function here. And you can also set this parameter here of how fast this exponential function is. And you're just going to pass this function for this Keras callback. And you're just going to train like the other model. And here I'm plotting the learning rate, the exponential decay learning rate. And for this last example here, for the cosine annealing, here we are going to use a function from Keras. It is already built in the Keras. So the cosine decay restart, you're just going to pass for this function the initial learning rate and the first decay steps. And just like we done before, I'm going to get the model here, compile, and here we're going, this is how our learning rate looks like. So after 10 epochs, it restarts. So here, just let's visualize the training loss for each one. You can see that plotting the training loss, you can already see more or less which decay that we applied. And now here we're just in the validation accuracy. You can see here, for example, the exponential decay was not the best here, but in this notebook is just to give a general idea of, for example, how to do those learning rate decays. Actually, there are like a lot of another learning rate decays. And for the last example, I'm going to show us some data augmentations techniques. And for this, I'm going to use again the CIFAR10 dataset. Here I'm going to load the dataset, transforming here the labels to categorical. We're going to use the whole training set as the training and the whole test set just for the validation as a validation set here. So we can, for example, define. Now we are going to define our functions for the augmentations to be applied. For example, here in this function, I'm randomly resizing the image and then scaling it back again to the original size. In this function here, we are applying a random crop. This functions here, it just uses here in the solarize function. It's going to apply this function is the image pixel, it's below the threshold, and it receives this value. And here we are going to define another function here, which we are going to apply random brightness and random contrast to the image, and random saturation and random hue. And here we're just clipping for it, so the images stay in this range. We're also going to define this function here that we're going to transform the image to a grayscale. And then this is just a function to randomly apply here. And then I'm just going to define this custom augmentation pipeline here. First you get the image, then you apply the flip random crop, the random apply, the color jitter, color dip, solarize. And for this training example, we are going to use the TensorFlow dataset. So I'm getting those X train and Y train from Terson slides. Then we're going to shuffle those data and map with this custom augment function. With this size with this batch size. So here we're just going to visualize some augmented images. You can plot. You can see that here for these examples, they are some augmentations are actually very exaggerated, just so you can see that it is very different here. Then we're just going to define our basic model that takes the input. Those images are 32 by 32 by 3. And here I'm rescaling the images with this function instead of when loading the dataset. And here we're just going to train with some data augmentation. We're just going to compile the model using the Keras optimizer here and fit the model here. As you can see, you're going to train. Here you're going to train with the data augmentation, and here you're going to train without the data augmentation. Here just creating another data set that I'm getting from X-train and Y-train, but here I'm not using the map function here for this custom augment. And then I'm just going to compile this model 2 here, that without data augmentation. And we can see the validation accuracies. For example, in this case, the dataset with augmentation was better on the beginning of the training, but at the end of the training, I don't think we can make some conclusions here. And here are the training losses. So this is just an example how you can implement your custom data augmentations like this with TensorFlow dataset. You can map a custom augment function that you call here. So this is just an example here, but normally we can use data augmentation in multiple cases, for example, to avoid model of overfitting. So this is the end of the presentation. I think I have some questions here. Should you always use some type of learning rate scheduling? Well, not necessarily, but it really depends on the task we're doing. If the model is too complex, or if you're going to train if you need for a long time, a lot of epochs, maybe you need a learning rate decay. And generally those, let's stop the presentation here. Generally those optimization techniques, they are not really clear. For example, you can say that for the optimizer, we can say that SGD and add-on are good choices. For the learning rate, it's an important decision. You have to find it, like at least the initial learning rate. If you choose a wrong one, the model will not train. And then you can test some learning rate, like after training your model, if maybe you can implement some learning rate, given that the model is learning something. And then the batch size is normally you are limited by your GPU size. Normalization, you can have another types of normalizations here. And for the regularization, I also did not present the L2 regularization, but I just presented the dropout here because it works well. And I think I can can pass to Leo to present the other her codes.
Hello,
Hi.
I'm back. And yeah, I'm going to steal some of Gabriel's time to show the code that I prepared. Yeah. So can we? Thank you. Oh, so you definitely cannot read that. I make this bigger. Okay, I think just one more. Now this is better. Yeah, this is readable. Looks readable to me. Okay, so I'll just keep that. This is preparing the environment because I was using our service here on USP, and what we're doing here first is loading the data sets. I'll ask Mossir to not chastise me for not making a validation set because, well, that's not the point of this code, right? So I'm just going to use the test set as validation. Please don't ever do that. Yeah, so here, I'll just look at my screen. Okay, here you can see I'm checking how the code is organized, then I see the range, and then I fix the range, add one dimension. This is, I should have explained, this is fashion MNIST. So if you know MNIST, it's like 10 classes, digits, and it's very easy to solve. And fashion MNIST is people trying to make a new kind of MNIST that is not as easy. So it's the same number of samples, the same number of classes, but all the images are pictures of clothes, and the classes are which kind of clothing item this is. And yeah, so we can go. And then I prepare the training set. I check how the target looks like, and it's, you know, the labels. So we just transform them to be one hot so that we can train with categorical cross entropy. And I will be using here Keras models, but TensorFlow training loops, just, you know, for code diversity. So I prepare a TensorFlow dataset here, which is very simple, just zipping the X and the Y from the train and the test set. And we make our big network. I'm calling this big because the other ones will be so much smaller, I promise you, because this is only 3 layers and it's not really that big, right? So we have 3 convolutional layers. Each of those 2 first layers is followed by max pooling, 64 filters for all of them, just really keeping it simple. ReLU activations, then we do flatten, dense, then 10 outputs and softmax activation to predict our classes. Yeah. I printed the model summary here, specifically because I wanted to keep this number in mind. So we have 105,000 parameters for this big network, and we are going to train it. So I made a model trainer in the TensorFlow sense, where we add a gradient tape. This would just record, this is just telling TensorFlow to record the gradients on everything we do here. Then I do a prediction, compute a categorical cross entropy loss, go out of the tape, get the gradients based on that loss, and apply the gradients with our optimizer. And our optimizer, well, it's an input to this function here. So I'll create it now, yeah. So we're just going to use the most default option possible. That's just an atom. I'll not even specify the learning rate, and let it choose the default learning rate, which I believe is 1 Wow, I don't know how to say exponential numbers aloud. It's 0.00030.1. Yeah. And well, we'll make our trainer and we'll set to use this first big model and this optimizer. And then I'll just do a simple loop. This loop we train, we get the loss, we print the loss if it's a step around 200. Every 200 steps, we're going to print the loss. Yeah, very simple stuff. We're going to shuffle the whole data set, and we're going to do batch 32 and 50 epochs, and we are going to have an accuracy of 70% for this one. Yeah, that sounds fine. I know this can reach 80%, so maybe if I tune the optimizer with a better learning rate and stuff, I know this a random network on Fashion MNIST can reach 80%. So we're around that. Okay. Now, what I'm going to do is I'm going to take the exactly same network, but I'm going to break each convolution into two. So this will be like separable, spatially separable convolutions. We're missing an L here. And well, it's really simple. We're just doing two convolutions. One is 1 by 3, the other is 3 by 1. We repeat that for each convolution, and everything else is the same. And just in parameter count, we are already getting some 15 to 20,000 parameters that we don't need anymore, we're not going to use anymore. And of course, the computational cost is much smaller. It's 2/3 of the original computational cost just to compute a forward on this network. So we do everything again, create an optimizer, make another of our model trainers, and we train it. And we actually got a better accuracy here of 80% using everything, pretty much everything the same. The reason for the better accuracy, I don't know. Maybe it's just random. Maybe if we look if we optimize better the optimizers on the first one, we should get to this 80% number as well. And finally, I'm going to take the first network again, and I'm going to break it, break each convolutional layer into two. And this time, what we're doing is a depthwise separable convolution. So if you remember, we need to do a custom kind of layer for the convolution. And thankfully, Keras already implements this. So a depthwise convolution in Keras is just apply the kernel to everyone and to every input map, and then don't do anything else. So you can see it's just, we don't even specify the number of filters because it's always just a single filter. Okay, and then we do a 1-by-1 convolution to actually make this into what we want the number of channels to be in the output. Yeah, so this is just making those images into code, right? And we keep everything else the same. You notice that the number of parameters here is dramatically smaller than what we had on the first one. And you also notice here how the depthwise COM2D here, it has very few parameters. So this is just a single kernel because there's a single channel as input. So it's just one kernel and one bias. So the kernel is 3 by 3, you have 9 plus 1, just 10 parameters for that convolution. And then we do the 1-by-1. And we train that, and we get an accuracy of 60% in this one. Now, this accuracy is, of course, much lower, but the model is also much smaller. So this is a choice that you can make when designing your network. If you're going to work on a drone, maybe you don't even want to use deep learning. But if you're working on a drone that can do deep learning, some kind of deep learning, maybe you want to have less accuracy. Well, it's very likely you want less accuracy and less computational cost. Not that you want less accuracy, but you get the idea, yeah. And that is the code. I had the very misguided idea that I was going to implement this with you. So I had an empty version of this notebook. But yeah, showing you the code is good enough, I guess, and then you can check by yourself. And yeah, Marcel is saying that those accuracy values are not exactly trustworthy due to random initializations. Yeah, that's true. I did run this a few times, so I'm not showing this here, but yeah, what you usually get for this one is 60. But as I said, the big model, you can get between 70 and 80%. That is all. And I guess that is all for the first part of the tutorial as well. I think.
Hello.
Yeah. Hello.
I'm back. Yeah, I'm back. Okay, nice. I have some questions, but I think we can ask in the second part of this tutorial in the afternoon, and because it's more general questions, like some advice for the students or people who are starting learning deep learning. So, and we have only 4 minutes. So I would like to thank all the presenters today, this morning, and we have more in the afternoon. And I would like to add that just before the second part of the tutorial, we will have the opening ceremony, 1 p.m. 30, I think so. And we will be back in the 2 p.m. 15, yeah? So I wish you well, and thank you so much, everybody, and see you in the afternoon. Thank you. In another link. Okay?
Oh, okay.
Yeah, okay.
Thanks.
Thank you. Thanks so much.
Bye-bye.
See you.
Bye.